All right. Hello, everybody. As I mentioned, I'm going to go through a couple of 2D vector problems. So we're going to start with a vector addition problem, and then afterwards I'm going to do a vector subtraction. Now, in the course notes, it talks about three different ways to kind of handle these problems, right? You can draw them using to scale super precise vector diagrams, but that's not something we're going to do in this course. Average measurement tools just won't get you as clean of an answer. So basically, there's really two ways that we're going to be solving these. Either you can solve it using trigonometry that you learned in math, so using your sine and cosine laws for non-right angled triangles and any of the trigonometry used. The other way to solve it is with components, and that's kind of the main way we do it in physics. Any way you choose to solve it is going to be correct, whether you choose to do trig or whether you choose to do components. But I'm going to demo this in components because that's something you might not be as familiar with. Okay, so let's take a look at our problem here. So we have a duck on a pond, travels 22 meters, and they travel 36 degrees north of east, and then paddles another 65 meters, 25 degrees east of south. Okay, so that means they're going in one direction and then they're going in another direction. So we're gonna have to figure that out. So whenever we have a problem like this, we always need to start by drawing a picture. Okay, so first we've got to draw this vector. So we're going north of the east direction, so we're headed in this way. So what I always like to do is start by I draw myself just a little compass so I can kind of figure out where I'm going. So this first one, 36 degrees north of east. Okay, so I am right. This is east. I'm north of it, 36 degrees. So it's going to be something like that. And this is our first vector. Okay, and then our second vector, going to do the same thing. Okay, and we have 25 degrees east of south. Now, something I should mention that's going to come up, this angle, north of east, it's measured from the horizontal angle. This one, east of south, is measured from the vertical. Now, this will happen sometimes. Generally, whichever one is closer, a smaller angle measure is what they'll use. But a lot of these shortcuts you may have learned in grade 11 for breaking a vector into components only work if the vector is framed from the horizontal. So this angle here, I'll just do a little aside. We are east of south, so we are starting south and then we are trailing east. So that would be right in here, right? 25 degrees. Okay. But I want this measurement. I want the angle based on the horizontal because it allowed me to use some shortcuts a little later. So I would just do, instead of 25 degrees east of south, okay, I could say that's 65 degrees south of east. Right, and 65 and 25 will give us 90. Okay, so I'll just scratch this out here. So this second angle, right, as we said, it is going to be, it's much larger distance, 65 meters, and it is 65 degrees south of east. So it would look something like this. with the angle from the horizontal measured there. Okay, the resultant vector is always a straight line from start to finish. Okay. So we are looking for this vector. So when doing components, what we want to do is write each of these individual vectors. Okay, we can break those into x and y components, right? This vector here, right, is the same as this x and this y, and this vector here, I can break it into these components. Okay. And then if I add all the horizontal components together and I add all the vertical components together, I can just get a simple right angle triangle that I can use to kind of assemble everything. Okay. So to break something into components, basically we're going to split things into x and y. So for x, dx is going to be, okay, we're taking the x component of this vector. Okay, so we're just using some basic trig here. The angle is adjacent to it, so we're going to use cos. So 36 cos of, whoops. So 22 cos of the angle measure. And as we see in the picture here, the x component is going east. So we'll just make a little compass here, and I'll say east is positive, west is negative. Okay, so this is going east, so I'll leave it as positive. And then the other angle measure, you see we have 65. The x component is adjacent to it, so it'll also be cos. So I can do plus 65 cos of 65. Okay. So these are both positive. So when I put them together, this will give me the components for my x direction. And again, make sure, especially if you're taking advanced functions, okay, your calculator, you might be using radians a lot. So make sure that whenever you're doing physics, you switch it back to degrees. So 22 cos 36 plus 65 cos 65. And I get 45.2686 meters east. Okay, and I'm just going to keep that number with 4 decimal places just to help for accuracy. Okay, then I'm going to do the same with the y components. Okay, now here I've got a vector, this small one going north, and this large one going south. So I'm going to make south positive and north negative, okay, just to make things a little easier. So this first vector here is opposite to the angle. So opposite means sine. So this will be, it's going north, which I said is negative. So negative 22 sine of 36 plus our other vector. Okay, the y side is going south, so plus, and it is opposite of the angle, so sine. Okay, so it'll be 65, because that's our distance, and our angle is also 65. So punch this in my calculator, negative 22 sine of 36 plus 65 sine 65. Okay. And this gives me 45.9787 meters. This came out positive. I said south was positive, so south. So now that we've taken these complicated vectors going in different directions, and we have now one single x and one single y. So we assemble that into a single triangle, and then we can just use normal Pythagorean theorem, basic trig to solve it. Okay. So when there's only two vectors, you might find it quicker and easier to break it into a triangle, find an angle inside the triangle, and use trig to solve it. This method gets, it's about the same amount of work. Sometimes you can do it a little bit quicker with trig if you're more comfortable with it. But I find as soon as you start adding 3 or more vectors, then components becomes way easier. To add a third vector here, it would just be one more plus, right? Or one more minus. Whereas if I added another vector here, I would have to draw 2 separate triangles and then solve both of the triangles to find the things that I actually needed. Okay? So just some food for thought there. Okay, so let's finish this off. So we've got 2 numbers, right? So we're going to be making a new triangle. So I always like to start with the horizontal line first. Okay. My dx, and then my dy was headed south. Okay. So that means that my resultant vector now is just going to be the straight line connecting the hypotenuse of these 2 points. Okay. So delta dt squared is going to be dx squared plus dy squared. So I had 45.2686. And then I had 45.9787. Okay. So put this in my calculator. So 45.9787 squared plus 45.2686 squared. Okay. Then I take the square root of that, and I'm going to get 64.5 meters. And if I look back, I am held to 2 significant digits. Okay. So my delta dt is going to be 65 meters. And I need a direction on this. Okay, so I'm going to have to use tan is opposite over adjacent. So dy over dx. So theta is the tan inverse of 45.9787 over 45.2686. Okay. And to 2 significant digits, we get approximately 45 degrees. So that means my final answer here, my resultant displacement is going to be 65 meters, 45 degrees, and then I look at my picture here. I went east first and then south. So I am south of east. Okay. And if you drew these in a different order, if you drew the y first and then the x, okay, you'll get the same numerical answer, but you'll be framing your angle differently. Okay. Because you'll be framing it from the south instead of from the east. Okay, but you would get the exact same answer that I got. Okay, so there is your final answer. Okay. So that is vector addition. Okay. And now I'm going to do an example of a vector subtraction. So something to note before we get it in, just some simple notation things here. So if you are adding a vector, right? So we know if we have vector A plus vector B gives us vector C, right? When we add these things, right? If this was A and this was B, then C, right, is the line from the start of A to the end of B. Okay? So let's say we wanted to rearrange this equation a little bit. Let's say we had vector B equals vector C minus vector A. Right? So what would that look like? We're now using C and A to try and make B happen. So how does that work? Right, how do we subtract a vector? Well, in vector notation, basically what this means is in order to subtract a vector, that is the same thing as adding the negative of the vector. And the negative of the vector is just the opposite. So if you take the normal vector and you add the opposite, okay, that will get you the vector that you're looking for. So for example, we were doing this here, right? This is, right, we had vector C, right? And vector A normally, right, looks like this, but we're adding the opposite to it, negative A. So negative A is the same thing, but in the opposite direction. So it's the exact same vector, but going the opposite way. And then we draw a straight line from start to finish, and we get vector B. Okay? So that's how vector subtraction works. Okay? You don't run into it a lot, but it does come up every once in a while, so you should be aware of how to handle it. Okay? So if you have to subtract vectors, you're going to add the opposite. And what that basically is going to mean for you is whatever direction the subtracted vector had, it's going to flip to the other way. Okay? So it's just kind of a quick little aside on how you would set something like this up. All right, so let's take a look at a problem. Okay. Subtract the vector 12 meters west from the vector 23 meters, 32 degrees south of east. So if this was vector A and this was vector B, okay, and it says subtract A from B, that means we are looking for B minus A, which would be B plus negative A. So that means we need the opposite of this vector. So if A is 12 meters west, then negative A would be 12 meters east. So just the opposite direction. Okay, now it's the same as before. Now we're just adding two vectors together. Okay. We're doing B plus negative A. So we have a vector that is 23 meters because we subtracted 12 from this one. So we're subtracting A from B, so B minus A. So B plus negative A. So I'll draw this vector for B here. And start with a little compass. Okay, I'm south of east. Okay, so I start east and I'm going a little bit south. Okay, so 32 degrees south of east for 23 meters. That's my first vector. And then my second vector is just a straight shot east 12 meters. So my resultant vector will be the straight line between these two. And now I'm going to solve it the exact same way I did in the previous question. You can choose to solve these again using trigonometry. If you like the look of that triangle and you want to figure out an interior angle so that you can use sine or cosine law, okay, feel free. I'm going to continue to use components. Okay. So for the x components, right, this first vector here, right, we can break this one down into an x and a y. This second vector is straight horizontal, so it only has an x component. Okay. Well, I can draw a little compass for myself. North, south, east, and west. Okay. All my x's are heading east, so east will be positive. All my verticals are headed south. Okay. So I will make south positive. Okay. So it's always good to have a little indication of what you want positive and negative to be. The default is north is positive and east is positive, but sometimes that's not helpful for solving questions. So it's better to do it like this, I think. So now I'm going to add these two vectors together. So I need the x component of my vector here. And it was drawn from the horizontal. My angle's from the horizontal, so I actually should have drawn the picture in like this. Okay, so I'm just going to do a quick little edit here. So we've got 23 meters. And the x is adjacent to 32. So that's going to be 23 cos of 32 plus 12. Okay, there's nothing to break down because this one only is horizontal. So 23 cos 32 plus 12 is going to be 31.5051 meters east. And for y, I only have one y component. Only one of these has a y vector that goes down. So it's going to be 23, and it's opposite of the 32. So that's going to use sine of 32. And there's nothing else to add here, okay? Because this one only has a horizontal component, so its vertical component is 0. So 23 sine 32 is going to give me 12.1881 okay, meters south. Okay, now same as before. I take these, I make a right angle triangle, and I'm home free. Okay. So first up, I've got dx, and then I've got my going east, and then I have my dy going south. So the only thing I need to find is the hypotenuse of this triangle. So that's going to be 31.5051 squared plus 12.1 1881 square. So 31.5051 squared plus 12.1881 squared. Okay. Going to give me 1,141.1211. And then I'm going to take the square root of that, which gives me 33.78 meters. And if I take a look, I am limited to 2 significant digits. Okay, so that's going to round to 34 meters. Okay, I need a direction. So I'm going to take tan of dy over dx. So theta is the inverse of 12.1881 over 31.5051. 12.1881 over 31.5051. And that's going to give me approximately 21 degrees. So my resultant displacement is going to be 34 meters, 31 degrees. I started east and then I went south. So south of east. Okay, and then that is it. Okay, so I've got my answer now. Okay, so again, you can choose to solve. If you'd rather take a look at this triangle, figure out one of the inside angles based on how everything looks. Okay, you can do that and use sine and cosine law to find the answer. Some people find trig easier. Personally, I like components, so that's why I displayed this method. Okay. Remember, when you are subtracting vectors, we don't have actual math for subtracting vectors. We add the opposite vector. Okay? So we add the vector going in the opposite direction. So b minus a is really b plus the negative of a. Okay? So hopefully that was helpful. I'll also include these slides so that you can take a look at them as well.